Thank you. Thanks for the introduction to Mars. And we've gone to one side of Mars. I'm going to take you back to the other side where InSight is currently, well, is left. And we'll talk about the seismicity of Mars as seen by InSight. And I'm going to try and tell you what, when, where, and why. There's a big caveat on this that I'm very good at the what, the when, and the where. The why was actually done by the wider InSight science team. I'm very much a hands-on seismologist, and I'm very good at finding Marsquakes, but a lot of the interpretation was done by the bigger team. So this is a huge team effort. So yeah, a lot of the work is not, well, the end of the work is not mine, but hopefully I can at least enlighten you a little bit on what's going on. So a little bit about me first. Just to start with, I'm trying to get rid of things and my cursor doesn't work. Anyway, I actually started out as an undergraduate astrophysicist, and then segued into seismology. And after my PhD, I spent a lot of time doing field work. I worked for Seis UK, and that saw me travel the world a lot and provide instruments to people like Derek. And I continued to do that for many years, including lots of much more exciting field work. For example, filming with the BBC for a children's programme called Deadly Dinosaurs, where we dropped rocks on cars. And I even had an opportunity to experience a little visit with, this was the prototype for the Rosalind Franklin rover. Many of you will be disappointed to hear, obviously, this didn't launch this year, but this was the original prototype, which I met several years ago. And the seismometer that was tested to travel on the Rosalind Franklin then is a version of the seismometer that is now on Mars. So it was my first foray into seismology on another planet. So it was several years after my PhD before I ended up here working on InSight. I'm just going to get rid of, I've got things over my screen because of the light and I can't get rid of them. There we go. I joined the InSight mission in 2018, just before launch. InSight is the first dedicated geophysics mission to another planet. The primary objective was to determine the internal structure of Mars, and we did meet that objective. The mission launched on May 5th, 2018, and landed on November 26th, 2018. And I was at the launch, although in a safe zone, and we could see very little because of fog. But I was there on the ground, and unfortunately, we lost contact with InSight on December 16th, 2022. Now, that was mission Sol 1440, so the 1440th day of the mission, and we'd only planned to be there for one Mars year, so about 700 sols. So we more than doubled our target mission, but it was still very sad to finally lose contact. We are still listening, and there is a chance we'll hear from it again, but it's more than likely that the mission is officially over. So this was InSight in the clean room before launch, and it's got a whole suite of instruments. So I will talk you through them, because for anyone who wants to know more about what you can do with this data set, it's good to know what we actually collected. So here we have a schematic of InSight. First of all, we have the instrument deployment arm. This in itself is not hugely exciting, though it did help us with a lot of experiments we did on Mars. It also has a camera which took a lot of very cool images. There's a second camera down here, the instrument context camera, which is a fisheye lens pointing out across the workspace, and allows us a view of our instrumentation at all times. We have a twins, the temperature and wind for InSight. So we took wind and temperature measurements on deck for a whole of the first year and intermittently throughout the second year. So we have a very good atmospheric data set. We have the rotation and interior structure experiment. This is called RISE, which is 2 X-band radio antennae. These, again, sent out pulses of X-band radio, which we measured the travel time and Doppler shift of to get an idea of the rotation of the planet. And that has proved quite successful. We had a heat flow and physical properties probe. This was designed to hammer its way 5 meters down into the subsurface. Unfortunately, it did not succeed at that, and this was the only instrument to not fully achieve its goals. It did take some heat flow measurements within the top 30 centimeters or so, but it was disappointing that it did not descend as far as we'd hoped it would. We also had an auxiliary payload sensor suite, which included a magnetometer and a pressure sensor. So as I said, combining that with the wind, the pressure and the wind gives us a really, really good atmospheric data set for this particular site on Mars. And finally, size, the seismic experiment for interior structure. I have left this till last because it is the most important, and that's not just me saying that, it was the primary instrument of the mission. So the seismometer was built, a combined French-Anglo instrument. So it's got a high frequency, short period instrument designed here in the UK, and a long period instrument designed in France, all integrated into a single unit. This was size when the last view we actually had of the seismometer before we covered it in its wind and thermal shield. So this was on mission day 66. It takes quite a while to deploy an instrument on another planet successfully, but it was a very good deployment. And this was our last view, our last photo taken of it on Sol 1421. So this was November 26th, the fourth anniversary of our landing on Mars. And you can see what 4 years of dust does to a seismometer, or anything really. This is the heat flow and physical properties probe here, and this is just one of the feet of the lander. So there's our seismometer, and it was really rather outstanding what it achieved for us over the mission. I'm going to talk you through some of the seismic data. We've had to look at it in, we learned a lot about how to interpret data from another planet. When we arrived, we had a beautiful set of velocity models that we thought would work, and we'd predicted what seismicity would look like, and it didn't look like what we thought it would. So what you've got here is a daily spectrogram. So this is one Martian day of data. This is actually Sol 923 of the mission, which was the 1st of July in 2021. So we have time across the bottom here, and here we have frequency. So being seismologists, we like to talk of frequency and period at the same time, but high frequency energy at the top, lower frequency energy down at the bottom. And we have sunrise and sunset marked here, and which helps delineate exactly where the day is, though you can tell from this plot, the colors here represent the power of the seismic signal. So this yellow bit here is where it's very windy during the day, and there's lots of turbulent noise here. And then we have a beautiful quiet evening period where it gets into more blues and purples. And then into the night and early morning, we see more laminar winds, which are still upsetting for us as seismologists, but not as bad as this really noisy bit in the middle. But it's not just noise. Sorry, there were some things there. Oh, other things I could talk about. Yes, resonances. Here we have, these are resonances of the lander. So the lander obviously vibrates when the wind blows, and these are thermally modulated. So you can tell different parts of the lander have different heat responses. The temperature on Mars changes by about 100 degrees a day. So there's quite a lot of stress on the lander thermically. There's an enigmatic resonance at 2.4 hertz. This is likely due to subsurface structure under the seismometer. We also see prominent glitches, these low frequency spike signals throughout the data. And these are due to stress release within the seismometer, or the cable to it, or the wind and thermal shield near it. And they are a right pain when you're trying to find Marsquakes. But it's not just noise. Like I said, there are a lot of Marsquakes within this as well. So here you'll actually see the signatures of half a dozen Marsquakes that we catalogued on this particular day. These are not particularly impressive Marsquakes, but they are pretty typical of what we saw. At the Marsquake service, which was one of the two ground-based services set up by the mission, the Marsquake service and the Mars Structure service. The Marsquake service was, which I worked for, was set up to catalogue the seismicity. So our job was to look at the data every day, find the quakes, and create a catalogue of it. Now, as you saw from the previous spectrogram, finding the Marsquakes is sometimes hard, cataloguing them is equally hard, and we settled on a cataloguing system where our events were named by their frequency, or their dominant frequency content. So I'm going to start with the highest frequency. We have very high frequency events, and these show dominant energy above 2.4 hertz, or at least with a 2.4 hertz signature, but with a lot of energy above, and that energy is dominant on the horizontal components. So here you've got Z, north, and east components for each of these event types. We then have two event types that are quite similar, high frequency and 2.4 hertz events. So as I said, we have this resonance at 2.4 hertz. It appears to be a ground resonance and it is excited by seismic waves. So we often see low amplitude signals of events at 2.4 hertz. And sometimes we see stronger events at this kind of frequency, which go up to about 4 hertz and down to below 1 hertz sometimes. And these are high frequency events. And now the more characteristically Earth-like quakes fall into two categories again, the broadband and the low frequency events. These typically have nice clear PNS phases. Broadband events have a signature at 2.4 hertz and low frequency events don't. Their energy is almost exclusively below 1 hertz. We also categorize our events by event quality. So this is basically a location quality. So that goes from A to D, where in a quality A event, we have a full location. So we have two travel times that we gain a P and an S phase or a PP and an SS phase that we can get a distance from. And we have a back azimuth so that we can get a latitude and longitude for it. Quality B, we would have two picks or one pick and one phase pick and a latitude longitude, but therefore not a complete solution. And then we get down to C's where we may have picks, but we're not certain by them, and we'll have no back azimuth. And quality D's, we often only know that there is energy there in the seismic bandwidth, but it doesn't necessarily, we can't pick phases, so we don't even have a distance for those. So of these events throughout the mission, we had mostly high frequency family events and about 80, 100 of the low frequency family events. So these are the traditional ones we can use for a lot of the work we've done on Mars. Now, when they occur,
it's 11 minutes now.
11 minutes. Okay. When they occur, it's very dependent on, well, to be honest, when we can see them is dependent on the noise. So we have these clear seasonal patterns. So spring and summer on Mars, we see a lot of quakes in this quiet evening period. But during the day, we see very few, although you will notice that we had 3 beautiful low frequency events that we can fully locate, which occurred in a relatively noisy period. So if they're big enough, we can find them. So where they happened, well, the distance, as I said, we can often get. We have 2 phases, a P and an S phase. We have velocity models. We can tell you where things happen. And we have distinct clusters of events. So our very high frequency events are scattered here. These are the triangles. Our high frequency and 2.4 hertz events form one very large cluster at about 25 degrees distance. We have a whole bunch of low frequency and broadband events around about 30 degrees. And then we have, again, clusters out here. Actually, we're not really sure what this cluster is. And then some of our furthest events out here. This is at Valles Marineris, this one here. But actually putting them on a map and not just a distance is very hard for the high frequency family. For the low frequency family, we have 31 fully located events. And like I said, we have a cluster at one distance, 30 degrees-ish, which happens to lie over the Cerberus Fossae, even, let's get the right thing here, Cerberus Fossae. So the region was originally thought to be a likely candidate for Marsquakes prior to InSight landing. This was from work from Taylor et al. And others. And so this is where we thought and hoped we might see seismicity. So it was a relief when we did see seismicity there. Recent imaging, even since that work, shows extensive boulder trails, which are likely triggered by ground shaking. And Perrin et al. 2022 mapped the Fossae system. So we've got the Fossae extend over 1,200 kilometers, and there's clear segmentation along the faults, and I'll show you close-up images of them. And so it seems to have formed in an extensional regime, and either from pure graben faulting or from fracturing above growing dikes at depth. So we're back to our dikes like we were in Valles Marineris. As I said, it varies along the length of the fossae. So we work along here from the northwest even down to kind of the southwest. And the other way, northwest, southeast. And you can see that we have different widths and depths of the faults as we go, and clear segmentation. And so there's lots going on within Cerberus Fossae. It's an amazing tectonic setting. And we, throughout the mission, I say we as in the whole science team, have looked a lot at these quakes. Initially, from the first year results, we had focal mechanisms for 3 quakes, which showed normal faulting in an extensional regime, so supporting everything we thought might be happening here. This was extended in 2022 by Jacobs et al., where we had 7 events within the Cerberus Fossae area, which again fit the geometry of the fractures and showed tectonic, extensional regimes. And there were 2 others which showed compressional faulting. And this, we thought mostly that our seismicity would be compressional before we landed, just from contraction of the planet. So to see these extensional faults was not necessarily what we thought we'd see. More recently, Simon Stahler has led a paper on the extension in Cerberus Fossae, and where we had locations for our low-frequency Marsquakes, Simon and his team also stacked the higher frequency Marsquakes, so those HF events we had, and they by stacking and comparing the expected energy on the horizontal component around the P-wave arrival, they saw an excess of energy pointing in the direction if they stacked them in orientation towards Cerberus Fossae. So it looks like the HF events also come from Cerberus Fossae. Now, as you can see here, the high frequency events are spread out along the entire length range of the potential of the graben structures, whereas the low frequency events, which were located using a variety of different, or a couple of different velocity models, the central model putting them right back here, which overlies the Cerberus mantling unit. Now, the mantling unit is interpreted to be the location of recent pyroclastic deposits. So what you see here is a symmetric outflowing around the fossae here, the fracture, whereas in most regions we see very one-sided structures on the sides of the grabens. Here we have it on both sides, and this unit is estimated to be less than 200,000 years old. So one of the youngest volcanic edifice seen at the moment. But there is no surface expression at the moment of volcanic activity, and yet this obviously is a potential source for what we're seeing. So the low frequency Marsquakes don't fit with patterns of terrestrial seismicity for volcanic edifices of that kind of age, kind of dormant volcanic edifices. We might see low frequency Marsquakes, so deep low frequency events with a slow rupture, and we'd see those in swarms. And we also see tremor events with long duration monochromatic signals. Now, we don't really see either of those. There are some early reports of potential tremor events, but there was nothing conclusive. And there are very few events like that in our catalogue. This may be partly due to the distance. We wouldn't see magnitude of 2 events at this distance, but the seismicity we do see doesn't fit at all with the patterns we would expect. And it's at depths of about 15 to 50 kilometers based on the focal mechanism fitting. And so this suggests an extensional stress regime and a warm source region, just the frequency content we see and the depth we see. So the data suggests, and the conclusions from the Stahler paper that came out very recently, is that there is ongoing opening of the Cerberus Fossae. And this is supported by other work. So this is likely that the high frequency events are right near the graben structure, and the low frequency events are at depth around the emplaced dikes. So if I was to be able to send other instruments to Mars, this is definitely where I would send more of them. And it shouldn't be forgotten that our largest, for a very long time, our largest quake and our most distant quake came from here in Valles Marineris. So that would be a cool place to go as well. So I think I'm probably up for time, aren't I?
Thanks. Yeah, thanks, brilliant, Anna. That was really fascinating. Are there any talks? Any questions?
I had a question. In the full catalogue of earthquakes that exists now, is there any hope to see something else in Valles Marineris? And is there also any hope of improving the accuracy of the earthquake location that you published and showed?
Okay, so first question, I don't think we're going to find anything, well, we don't have anything that would be quite as far out as Valles Marineris. There are some events that we don't have particularly clear phases for which alignment is being done. So phase alignment, like envelope alignment, based on the shape of the S wave envelope or the P wave envelope. Most of the distant ones, we don't have both phases. They're just aligning on one phase, and that is pulling some of these events further away. So we're wait and see on that one, but there was nothing clearly clearly in Valles Marineris. As for improvements of locations, yes, there is more work being done on finding back azimuths, and we are doing joint inversions for the structure. So we have mantle models that have now been verified. We've got 2 or 3 events that are known, or 2 known distant impact events. So we have very precise locations on those. So inversions are being done for the mantle structure from those, and we have those had surface waves, and we also had a very large Marsquake May last year, which has beautiful surface waves from which we're getting crustal models being formed. So as those come through in the next 6 months or so, we will be looking to relocate a lot of the whole catalogue based on the new velocity models. So I expect locations to improve in the next 6 to 18 months.
Okay, thank you very much.